Okay, so let's move to the last part in lecture 4 is the non-stoichiometry effect in ionic solid materials. So what's the non-stoichiometry effect and know how can we know whether the non-stoichiometry effect happen in our ionic materials? So the easiest way would be just perform experiments by just measure the diffusivity of your interesting ion at different temperature and have this curved line. And after fitting, you can you can get you can fit it with three straight line with three different slope. And at high temperature regime, as you learned before, will be intrinsic Ch4 defect formation uh, Ch4 defect dominate, and at the low temperature will be the dopant dominate, and in between, this will be non-stoichiometry effect dominate. So in order to know the easier whether there's a non-stoichiometry effect happening in your materials, the easier way just perform experiments made by measuring the diffusivity of your interesting ion at different temperature and fitting this curve. So now the example I want to show you here will be the what we have here is we have an iron oxide ionic material, then I dop with titanium dioxide. So here the iron with two positive charge and the titanium ion with a four positive charge. So can you try to formulate the DFE at intrinsic regime and also at dopant regime? Then, so probably next I'm going to, so after this, we will move to the non-stoichiometry effect in details in next slide. So let's deal with this one first. At high temperature, the Ch4 defect dominate. So you can formulate these results. We don't have any vacancy, then generate the Ch4 defect. So we will generate a pair of vacancy VFE and VO. So in order to formulate the DFE, so we want to know the fraction of vacancy at iron side. So based on these results, we also know the K as a rate constant in the Ch4 defect or for the Ch4 defect formation can be write down like this. This times this equals to exponential negative or minus the Ch4 defect formation energy divided by KT. And because this equals to this, so I can know the fraction or the vacancy fraction at iron side equals to at oxygen side equals to this. So I can easily formulate the diffusivity of iron ions expressed like this one. This term is n times the dV and times F. So when you log these equations, so the slope will be this one, right? This one plus this one in enthalpy term. So will be like this. You have the migration energy and also the Ch4 defect formation energy divided by 2. Then how about the diffusivity of iron ions at dopant dominant regime? So as you learned before, when you dope titanium dioxide into iron oxide, the titanium have 4 positive charge and will be occupied at the vacancy with 2 negative charge. So 4 minus 2, so you have the 2 additional positive charge here. And the oxygen will be located at oxygen vacancy, occupied oxygen vacancy. And in order to reach the electrical neutrality, you will have a vacancy at iron site with 2 negative charge. So it's easy to determine what kind of vacancy you have here. Is iron vacancy is a vacancy at iron side or oxygen side, depending on this. This is a two positive charge, right? For sure, there's a negative charge here to reach the neutrality. So you will get the vacancy at iron side. So based on this, and also based on the previous deviation, you know at the dopant dominant region, the vacancy at iron side will be equal to the fraction of dopant. So you can easily formulate the results is the TiO, the concentration of fraction of TiO2 times the dV times F. So when you take a log on this equation, so the slope will be only this term, right? So you got the slope will be proportional with the migration enthalpy of the vacancy. So now we still have a non-stoichiometry region in between, right? So what's this? So let me show you what's this. So when we talk about the region 2, the blue one actually is region 2. So non-stoichiometry actually is how to determine whether yes, probably you will have this fitted with this a straight line with certain slope, and the other criteria you need to know to determine whether there's a non-stoichiometry effect will be the ionic material you talk about. For this case, the iron is with two positive charge, right? So what's non-stoichiometry means? Let's also have three positive charge ion coexist in these ionic materials. So this kind of we have iron with two different charged. Under this situation, we call it a non-stoichiometry effect. But some people probably will ask, Professor, why you don't consider the with one positive charge? Because the electronic state for iron is not easy to have it's not easy to carry with one positive charge. So in most of cases, it is two positive charge or three positive charge. Okay. For example, like the other material, titanium dioxide. For titanium dioxide, titanium is dioxide with four positive charge, right? But the other commonly charge will be the positive with three positive charge for the titanium. So titanium oxide is easy have a non-stoichiometry effect also. Okay, so let's back to here. So we want to show you how to analyze the slope for this non-stoichiometry effect. So let's try to step by step. So my question would be, yes, non-stoichiometry effect. That means some iron with two positive charge, due to some reason, it converted to three positive charge. So that will lead the non-stoichiometry effect. So how or why some iron with two positive charge will lose the electrons to become the three positive charge ones? So the equation will be like this, right? Iron with two positive charge, it loses the electrons and become have three positive charge one. And because it loses some electrons, it lose the electrons. So which means some atoms or molecular receive these electrons, right? And become the ionic atoms. So in this case, you need to have oxygen. Can be the oxygen or other molecules who can receive the electrons. So in this case, we flow the oxygen into this furnace. Okay, so we have the oxygen, and oxygen will receive the electrons to become the oxygen ionic atoms. So based on this, you just summarize. You just end these equations up. So what you have here is the iron ions with two positive charge, then we flow with the oxygen, then some iron were converted to three positive charge, and we have the oxygen ionic atoms. Okay, so if you want to know really what really happens in this ionic material, so let's the figures you can check figure A and B. So this is the iron oxide before non-stoichiometry effect happened, and this is the oxygen atoms which decompose from oxygen O2. So when this neutron oxygen occupy this location, it is going to take two electrons from this iron and also this iron. So this iron will become a three positive charge, and to reach the neutrality, it also will get the vacancy at the iron side to reach the neutrality, electric neutrality. So this is what really happened inside ionic materials. So each oxygen atom take two electrons from two iron with two positive charge ion and leave a vacancy. So when we try to rewrite this chemical equation, you can write like this. We have ions at iron side with neutral charge, and we flow the oxygen. Then what we have here is some iron with three positive charge will locate at iron side. Because this vacancy at iron side is only it have two negative charge, and this have a three positive charge, 3 minus 2, so you have one positive charge here. And oxygen always stay on the or will stay or occupy the vacancy at oxygen side, so O at O neutral charge, and you will have generate the vacancy at iron side with two negative charge to reach the neutrality. So based on this equation, so the purpose here actually is just formulate what's the fraction vacancy fraction at iron side, right? Because we want to decouple, we want to know the DFE. Okay, so based on these equations, some people will write down or rewrote or organize them become here and just delete this term out. So what you have here is we have the oxygen, and in before non-stoichiometry effect happen, then after this effect happens, the oxygen at oxygen side, and we will have a general vacancy at the iron side, and also we have the two holes at the iron side. These two holes means this hole, one positive charge times 2, so you also have one positive charge times 2. So you got this equation. So based on this equation, we can formulate the rate constant under the equilibrium condition is this times this divided by partial pressure of oxygen. And don't forget the order is 1/2. And for this times this, the order is also 2 put here. But some people probably, so this one will be equals to exponential minus formation energy divided by kT. This formation energy will be the non-stoichiometry effect of formation energy. And by the way, some student asked me about why we delete this term out from here to here and did not delete this term. So the idea here is because on your left-handed side we have oxygen, right? If I delete this term, the oxygen go to where? So this just want to point out the oxygen was at the oxygen side, is at the oxygen side. But this term actually is not involved, this term is nothing related with rate constant here. But if you you still can put this F iron at iron side at the bottom, and the oxygen at oxygen side at here, but the fraction for this one and this one is belongs to one, so you got the one here and one here, so nothing. You are not going to change anything on the rate constant this term. So why this is one and this also one for because most oxygen still occupy the oxygen side, and the iron iron occupy at the iron side, so the fraction is near to one. So you can just put you can OO here, fraction of OO and fraction of FE. So you can rewrote like this. And based on this equation, the purpose here is you want to know what's the VFE, the vacancy at iron side. This is what we want to know. So based on this equation, we know the relationship between this and this one, right? So what's the relationship? The mole will be, we have 1 mole of vacancy at iron side, then we will have 2 mole of holes, right? So we have 2 here and 1 here, so you need to times 2 to get the equal. So you got this relationship, and just substitute the fraction of the whole with 2 VFE. So you got a 4 vacancy at iron side to 3. So in order to get this the VFE, it's you will get this relationship will be proportion with the exponential negative activation energy divided by 3 kT, and also don't forget this term is a partial pressure of oxygen. So now we already know the vacancy fraction at the iron side, so we can successfully just substitute this term to get the DFE. So when you try to know the slope for this non-stoichiometry effect, will be included this term, right? Enthalpy this term, and also the migration energy part. So including the migration energy and this term. Okay. So the other thing I want to remind you will be, take a look here. We observe on this non-stoichiometry effect, the vacancy at iron side is proportional with partial pressure of oxygen. So what this means, when you try to increase the partial pressure of oxygen, what will happen? You will have higher vacancy fraction at iron side, right? This increase and diffusivity will increase. So this blue line, or when you try to increase the partial pressure of oxygen, so this line, straight line, will move to upward, right? So will be get to upward. You are going to judge the slope, because the slope is related to the formation energy and also migration energy. So when you change the partial pressure of oxygen, so the only thing you change for in this plot is the intercept. So will increase, go this way, right? So in the same idea, if you decrease the partial pressure of oxygen, so this will be, this blue straight line will go downward. So when you decrease the partial pressure, so for decrease to 0, then you will back to what? You will back to this curve. Also only below only have intrinsic and dopant dominate ionic materials, right? So this is just hope you can keep it in mind. So the other information here is, it turns out based on this relationship, you know that when you the VFE is proportional with partial pressure of oxygen. So application for this type of material, what type of material is have a non-stoichiometry effect? This type of material always be used as a oxygen sensor or gas sensor because the vacancy at iron side will be proportional with the partial pressure of oxygen and also will be proportional with the diffusivity of iron. And usually this will link with the conductivity of these ionic materials. So in this case, lots of people use this type of material to be a gas sensor, not only the oxygen, sometimes the nitrogen sensor, and so on. And regarding to the dopant, some people also ask me about when you try to increase the concentration of dopant, this red straight line will also move upward or downward. Okay? Okay? Okay, so I'm going to give you a quick summary here. So, in the first section, we show you how to link the the diffusion phenomena and in the macro scale and the diffusivity in micro scale, right? So we after several deviations, we get the diffusivity equals to the total jump rate times the mean square jump distance. Oh, sorry, it's a mean square jump distance divided by 6 times correlation factor F. And Z, actually, total jump rate can be considered as a Z. It's a coordination number times the atomic jump rate along one direction. And the small r actually is correlated with crystal structure, is related with lattice constant ABC. And for interstitial and vacancy, the correlation factor F equals to 1. And when we talk about the vacancy mediated self-diffusion, the diffusivity of the host atom will be equals to XV dVF. And for the interstitial C mechanism will be XI dIF. Because both case is the fraction of vacancy and fraction of interstitial defect will significantly affect the diffusivity of the host atoms. And you also need to know how to determine the vacancy formation energy and migration energy in experiments, okay? And in the second part, before the second part, actually, we talk about we ended some dopant at the inside the substitutional site into the substitutional site, and we want to formulate the diffusivity of the solute atoms. So based on this, and also the diffusion mechanism belongs to vacancy mediated one. So based on the solute atoms, so there are 3 different types of atomic jump frequency in these materials. And first of all, we need to consider which is the rate limited jumping process. Then you can easily write down the diffusivity of the solute atom. And in the second sections, we move our materials from metal to the ionic solids. And the diffusion mechanism we talk about here is also the vacancy mediated one. So in ionic solid materials, there are 2 methods to generate the vacancy. The first one we call the Schottky defect, which you can generate a pair of vacancy. And the other one is the Frankel defect, which means the cation or anion move to the interstitial defect and left a vacancy. In this case, we call it as a Frankel defect. So to get the diffusivity of the cation and anion in this case, first of all, you need to formulate the charge defect equation and to clarify or determine it belongs to vacancy or interstitial diffusion mechanism. For vacancy one will be focused on the Schottky defect, and interstitial one will be the one we consider will be the Frankel defect. Okay, then you need to think about are there any dopant inside this dope into this ionic material? So it belongs to intrinsic material property or extrinsic material property or both. And next, based on the iron, the electronic state, you can uh, you can you can have some idea about whether there's a non-storage armature effect happen in your ionic materials. Then we believe you can successfully to get the fraction of the vacancy to get the XV or XI. Then you have chance to completely formulate the diffusivity of cation or anion in your ionic material.